Hi, today we're going to start a really brief two-lesson mini unit, if you could even call it that, on limits. And today we're going to take a look at using limits to find tangents. Now, if you're going on to calculus, this is going to be kind of a valuable little refresher of what we were doing to get you into that course, since I know many of you will probably take it next semester. And for those of you who aren't taking it at all, at least you're going to get a good little bit of review from the first few units of this course, or at least refresh some of those ideas and bring them back as we talk about limits themselves. So limits are actually pretty much exactly what they sound like. It's a limit as you approach something. Yeah, I think that makes sense. If it doesn't, let's take a look at some stuff now. Okay, so you may recall reciprocal functions, which look a little bit like that first example. F at x equals x squared minus 1 over x minus 1. And I'm going to make note that we can actually factor the top and the bottom. That becomes x minus 1, x plus 1 over x minus 1. Now, nice for us, those two x minus 1's cancel out top and bottom, and I'm left with a very simple linear equation, x plus 1. However, it's x plus 1, but x is not defined at x equals 1. So we have our graph there to the right, and you may recall from previous lessons that it has something called a removable or a whole discontinuity. So it looks just like the linear function x plus 1, except at that one little annoying spot. And because of that, we can't say what the value is when x equals 1, which is really kind of weird because, I mean, looking at that graph in every way, shape, or form, you kind of intuitively know what the answer is going to be at x equals 1. The answer is going to be 2. But it isn't. It's undefined. But no matter how you approach it, as you get closer to it, it looks like it's getting closer to 2. And as we come from the other direction, it looks like it's getting closer to 2. And it is actually getting closer to 2. And you can test that by punching in numbers like 0.00000000000. No, wait. Yeah, no, 0.9999999. That's it. Plug in 0.99999, you get out 1.99999, which is really, really close to 2. And if you're on the other side, you can plug in 1.0000001, and what you're going to get out is 2.00001, and it's also very close to 2. So it definitely appears to be approaching 2. And because of that, we say that there is a limit that exists. And there's our notation right there. We read this right here as the limit as x approaches 1 of f at x is 2. So we're not saying that f at 1 is 2. We're saying that f at x as we approach 1 is 2. And f at 1 itself is undefined. Now, sometimes limits are defined at their points, and sometimes they aren't. And if they aren't, that's okay. We can still talk about what they're going to approach as they reach certain values. Now, in calculus, you'd go into much more detail on limits, and you'd actually solve them or work with them in much more unusual circumstances. But for now, I just want to get the idea across of how limits work. So let's just start by looking at the limits of some pretty straightforward functions. The limit as x approaches 5 of x squared. Well, is x squared defined at x equals 5? Because if it is, that will be the limit as we get there. And it is, so we just say that that's equal to 25. This second one is going to confuse most people. That's okay. Let me explain it. The limit as x approaches 1 of 6. I want you to take a second and think about what that's saying. And hopefully you're getting the answer 6. 6 is just a constant, y equals 6. Y equals 6 when x is 0. Y equals 6 when x is 3. Y equals 6 when x is 27.2. Y is always equal to 6 no matter what x is. So the limit as x approaches 1 of 6 is just 6. Because technically in that function, f at x equals 6, x approaching 1 or x at 1 is 6. So it's a weird one, but hopefully it makes sense. Now part C is similar to the one above. What we can do is say the limit as x approaches 0 of that, x squared minus 5x plus 6 over x minus 3 equals the limit as x approaches 0. And we can factor the top and the bottom. Sorry, the top, but the bottom's already factored. So on the top, I think we're going to get x minus 3, x minus 2. And you'll notice we still write the limit as x approaches 0 at the beginning because we haven't actually done the limit yet. And this is a fairly common error that students make in calculus, is that they will either get rid of the limit notation at the beginning of the line before they've actually done the limit, or they will leave it in after they've done the limit. It's an instruction like a square root sign. You can't just get rid of the square root sign before it's done its square rooting, and you can't just leave it in after you've done its square rooting. Okay, so now I can cancel the x minus 3's out, and that becomes the limit as x approaches 0. Sorry, I goofed on those. This should be the limit as x approaches 3. The limit as x approaches 0 is actually a very common one to do. That's why I write it by default. The limit as x approaches 0 of x minus 2 with the restriction x cannot equal 3 on it. Well, what is x minus 2 when you plug in 3? The answer is 1. But we said x can't be 3. And that's true, x cannot be 3. This function, or this original question right here, is not asking us to evaluate that function at x equals 3. It's asking us to state what what the limit of that function is as x gets closer and closer to 3. And if you do that, you'll actually see that it is pretty close to 1. Okay, the last one, we're going to kind of do this one a little bit more intuitively. You already know the result to this just from talking about domains and ranges and end behavior. What's going to happen to 1 over x as x approaches 0? Now, technically, it is not defined at x equals 0, but what will it equal? And this is where people are going to have a hard time. It does approach infinity, sort of. Well, if I plugged in 0.000001 on the bottom, I'd get a number that's getting very, very large. But it's also approaching negative infinity because I could approach 0 from the other side and do negative 0.000001. So there is actually a way to do this, and this one actually has no solution, which I know is going to bother people. So what I'm going to do is just point out that you can actually do this question just a little bit differently. You have to really rephrase the question, not the answer. To rephrase the question, what I can say is, what is the limit as x approaches 0 from the positive side of 1 over x? And what is the limit as x approaches 0 from the negative side of 1 over x? Well, if x is a little bit positive but close to 0, then this will approach infinity. And if it's a little bit negative and approaches 0, it will be negative infinity. And you probably recall this graph that looks like this. And sure enough, as x gets close to 0 here, we go up to positive infinity, and if it gets close to 0 there, we go down to negative infinity. So it wasn't so much our answer needed to be modified, the question itself needs to be modified if we want to answer it. Some limits exist regardless, and some limits only exist one-sided, or they're different on both sides. So we have to approach the number from two different directions. All right, now that I've thoroughly confused you, let's move on to using the limits to find the tangents of curves, which is what this lesson is all about. Now, I'm going to actually ask that you pause the video for just a moment so that you don't hear me talking for a little while. And I want you to look at that diagram and try to figure out what it is saying. See if you can make sense of it. Don't worry about any of the text on the left. just focus on the diagram. In fact, I'm going to zoom in on it and give you some time. I'm going to hit pause and come back. Actually, I don't have to hit pause. I just keep going. But you hit pause and come back when you're done. And then I will try to walk you through it a little bit more. Okay, assuming that you did that, knowing that you didn't. What this graph is saying is that we have some point. I'm going to draw on the graph and I'm going to erase it like, I don't know, a million times because it's going to make a huge mess. I have some point here, right there, P. And I've got some other point, Q, up here. Okay, now P is going to have coordinates of A and F at A, since this is the function graph F at X. So what it's saying is that I have this A value down here that I plug in for X, so its coordinate will be A F at A. And then I'm going to say, I'm going to go over just a little bit. I'm going to call that H. So I'm going to go over H units, and then I'm going to find another point. And its coordinate Q, or sorry, we're going to call it Q. Its coordinates will be X plus H, because that's its X value. And then F at A, sorry, A plus H will be its X value. F at A plus H will be its Y value. Okay, now we have a little triangle right here. And the slope of the diagonal part should be equal to the rise over the run. Well, the rise is the change in Y values of the 2 points. So F at A plus H minus F at A. And the run of the slope is going to be H, because it's really X plus H minus A plus H minus A. And what that means is that the secant between between points P and Q will be represented by that equation right there. The slope of the secant is a change of y over a change of x. We often say delta y over delta x, which is the change of y values, f at a plus h minus f at a, over the change of x values, a plus h minus a, which is then just h. Now what we want to do is use limits, or the idea of limits, to say, well, what happens as this point Q moves closer and closer and closer to P? It's going to get so close to P that the difference between P and Q is essentially negligible. And then we just have the slope at point P, which is a tangent, as opposed to a secant between P and Q. So we're just letting that point get really, really close. And we faked this with secants way back when we were working with polynomials and wanted to find the slopes. That's how we did tangents way back then. To be technical, I mean, this is essentially what we did. We let h go to 0 as we looked at f at a plus h minus f at a over h. Now, I will point out that in the textbook, if you look it up, they refer to that equation that I just showed you right there as being equation 2 or method 2 or formula 2, whatever it is. There is a different one that's slightly different. It's just a slightly different way of looking at the diagram. It is an equivalent expression, but I find it more difficult to use, so I just stick with this one. And I do want to point out, for those of you who are going to take calculus later, that you're going to do something called a derivative. And the derivative of function will give the slope of the tangent. And the derivative is defined, the way that we write it, the way that you would write a derivative. I'm going to do this by hand so you see the difference. If I want to do the change of slope of y, I do dy by dx, is what they call it in calculus. Technically, they're not doing d's, they're doing something called a delta, which looks a little bit more curvy. Oh, sorry, that should be dy by dx. But delta y by delta x. They'll often, though, call it dy by dx, just because they tend to look like a d when you're handwriting them. I like to actually point out that it is really delta y over delta x, and that this is a lowercase delta. And if you recall, the normal slope equation between any 2 points delta y over delta x. Notice it's the same word, delta. This is a capital delta. And so in calculus, what we're really doing is still looking at this equation, but instead of looking at a change of y over a change of x, we're looking at a little change of y over a little change of x. And we call that a derivative. So if your teacher in calculus says dy by dx, tell them it's delta. At the very least, even if they do it that way, even if you do it that way, and even if you call it d, if you in the back of your head know that it's a delta, I think it will help you understand why you're doing what you're doing. You're looking at small changes of y over small changes of x. Out with the theory, in with the practice. Use limits to find the slope of the tangent of the function y equals x squared plus 2x minus 1 at x equals 2. Okay, so we said that the slope of the tangent, I'm not going to bother putting subscript tangent on there. We know what we're doing. The slope of the tangent equals the limit as h approaches 0 of f at, now here in this case, we're looking at x equals 2, so that's our a value. So we're looking for f at 2 plus h minus f at 2 over 2 plus h minus 2, which is just h. And I could have automatically jumped to that because that's what the formula is. But just in case you're wondering where that h on the bottom comes from, it's not magical. It's just a plus h minus a. And now for us, that becomes the limit as h approaches 0. We have to keep writing it until we've actually done the limit, until we've figured out what the answer is. If I plug in 2 plus h into my formula, I get 2 plus h squared plus 2 plus h minus 1. So that's my f at 2 plus h minus f at 2, which is actually a lot shorter to write. That's just 2 squared plus 2 times 2 minus 1. All over h. So now, still doing the limit, haven't actually calculated anything yet or worked with it yet, so it stays. And on the top, I'm going to expand that and see what I get. And I think the answer is 4 plus 4h plus h squared plus 4 plus 2h minus 1 minus 4 minus 4 plus 1, if I take that negative in front of the bracket into account. Okay. So now I'm going to collect like terms. I have an h squared there. I don't want to miss any. H squared, 4h, 5, 6h. And then 4, 8, minus 8, minus 1, plus 1. Those all cancel out. And then I still have the h on the bottom. And now what I can do is actually divide top and bottom by h. Whether or not it exists at h equals 0, and technically it doesn't have to, I can still say that since we're just looking at the limit and not the value of h equals 0, h can be 0 for our purposes, or at least we can divide by h, since we're letting it get close but not touching. So normally we can't divide top and bottom without putting a restriction on. Here we're not saying that h will ever be 0. It's fine if it isn't. We're just saying it's getting close to 0. So h squared over h is h. 6h over h is 6. And now I have the limit as h approaches 0 of h plus 6. Well, when h goes to 0 there, I'm just left with 6. Now I no longer write the limit as h approaches 0 at the beginning because I've actually dealt with it. And that's my answer. The slope of the curve to y equals x squared plus 2x minus 1 at x equals 2 is 6. A little bit roundabout way of doing it, but I want to point out that back in Unit 1, we would have done it by just saying, what's the slope of the secant between 2 and 2.01, and then rounded it off a little bit. Here, we didn't need to know what the second point was, and we still got an answer. So we just said, at 2 and a little bit, letting that little bit go to 0, letting the little bit disappear. And we got a slope out. That is kind of cool. And what you'll learn in calculus is, well, in calculus you'll start with this, and then you'll learn how to take advantage of it and harness it, and then do derivatives without limits, which will make your life super fast and super easy. But since you're not in calculus, I'm going to make you do it the long, tedious way. Use limits to find the slope of the tangent to the function y equals 1 over x minus 1 at x equals 2. All right, slope equals the limit as h approaches 0. And this time, just to save a line, I'm going to say it or think about it, but I'm not actually going to write the whole thing out. The bottom of the formula says h. The top of the formula says f at a plus h. So this is going to be 2 plus h in this case. So this will be 1 over 2 plus h minus 1. And then subtract f at 2, which is 1 over 2 minus 1. Equals the limit as h approaches 0 of 1 over 2 plus h minus 1 is just h plus 1, or 1 plus h, doesn't matter, minus 1 over 1 is 1, all over h. Okay, so now what I'm going to do is multiply top and bottom by 1 over h. And what that's going to do is make my fraction on the bottom go away. And on the top, I'm going to be left with 1 over h times h plus 1 minus 1 over h. Getting closer. What can I do next? H approaches 0. I can find a common denominator. And what I'm going to do is multiply the second fraction by h plus 1 on the top and the bottom. And then I can put those together. And I have 1 minus h plus 1, which is 1 minus h minus 1. So that would just be h over h plus 1. And I can cancel out an h on the top and the bottom. Again, technically I can if h is 0, but we're not going to be 0. We're going to approach 0. And then finally, as h goes to 0 in that function, 1 over h plus 1, that just becomes 1 over 1. So now I've evaluated the limit. I no longer write the limit as h approaches 0 at the front because it has been dealt with. The h is gone. Ooh, I made a boo-boo. I made a little boo-boo. It's just a little boo-boo. That's okay. I think I said it right before, but I didn't do it. In the third last line up here, this minus sign should have affected that h. So the answer actually should be -1, not 1. If it looks like it jumped, the video jumped a little bit, it's because I came back to edit that later because it was weighing on me why it had a positive slope when it should have had a negative slope. And that was it. I just missed a sign. So anyway, it's going to jump back to just +1 for a second as I scroll down to question 3, but ignore that part. Third one. This one becomes a little bit more interesting. The limit as h approaches 0, m equals, the slope equals the limit as h approaches 0 of the function at 9 plus h minus the function at 9 over h. So essentially, there's the formula. I've plugged in my values for f at a plus h and f at a. Okay, tricks we can play. So what I'm going to do on the top and the bottom, just trust me for now. Here's what I'm going to do top and bottom. I'm going to multiply by the conjugate of the top part, which basically means the same two terms, 9 plus h. You know what? Actually, let me do one more line first. Let me make that. The root 9 is just 3, so let's get rid of that. That'll make our lives a little bit easier, a little bit prettier anyway. I'm going to multiply by its conjugate on top and bottom, which is root 9 plus h plus 3. Root 9 plus h plus 3. And let's see what that does. On the bottom, I'm going to have h root 9 plus h. Oops, shouldn't be a bracket yet. 9 plus h plus 3. And on the top, when I multiply two conjugates like that, it ends up, those are the factors of a difference of squares. So if I put them together, I actually get a difference of squares, which is going to be the square of root 9 plus h, which is just 9 plus h, minus the square of 3, which is 9. Okay, so on the top, I have 9 plus h minus 9 is h. And on the bottom, I have h times root 9 plus, oh, what the heck was that? 9 plus h plus 3. Well, I can cancel out the h on the top and the bottom. So this becomes the limit as h approaches 0 of 1 over root 9 plus h plus 3. And now it's in a form where canceling the h or letting the h go to 0 is no longer ambiguous. It has a direct answer. That just becomes 1 over root 9 plus 3, which is 1 over 6. So the slope of root x at x equals 9 is just 1 over 6. And different functions, some of them are, like this one is a little bit trickier. We need to get that conjugate trick in there. Some of them are easier, some of them are harder. I'll try to give you ones you can do. There's some limit problems there. I'm going to point out that the limit questions, this is not the regular textbook, so there's actually a textbook, a bit of a textbook file that's called limits. I think more specifically it's called limits text with answers, and you can find the questions there. Also, it does say in several of the questions that that you can use the different methods, method 1 or method 2, to find the limits. Just do the way that we did it today. Don't worry about doing it any other way. And oh yes, there is one challenge problem beyond what's in the book that I think is an interesting one to look at. And it's, can you figure out what the limit as h approaches 0 of, find the slope of f at x equals sine x at point A. I'm not even telling you what point. I want the answer to be a function instead of a specific value. So can you find a function that represents the slope of sine x? Is essentially what I'm asking you to do. And I've given you a little bit of a hint there. The part that we can't derive from scratch yet, or shouldn't try to derive from scratch yet, is that the limit as h approaches 0 of sine h is h. Basically, if you take a look at the graphs of y equals sine x and y equals x and zoom in on them, you'll see that as it goes through the as it goes through the origin, the the slope of the sine graph is exactly 1, and it basically, they're the same thing over small interval around 0, and since we're looking around 0, you can basically replace sine h with h. That's the only thing I think you need to know to solve that one. Anyway, I'm going to stop there and give those a shot, and I will see you in the next lesson.